Hello again, eighth graders. It's Mr. Pouts. Um, Today we're going to do a video for section 2.8 or 2-8, which is again about proportions, but we're going to also talk about similar figures. So our goals that you should write down on your goal sheet. Please pause it and write down these goals. There's two for this lesson. The first one would be to find missing lengths of similar figures. And the second one would be to use similar figures when measuring indirectly. So you'll find out what those mean. Just please make sure you write those down and then self-assess yourself afterwards. All right, so we're going to talk about how we're going to use similar figures or proportions to find missing things. So here's some vocab for today. First one is, what are similar figures? You may or may not know this, but we're going to use those today. So by the way, I think this one, scale, is definitely one of the key vocab words for this chapter, in case you were wondering. But similar figures are simply figures having same shape, but not necessarily the same size. So I'm going to show you right here. We'll say, so write that down, same shape, but not necessarily same size. It could be this triangle and this triangle. Both right triangles, they look like the same, only one is bigger than the other. Okay, those are similar figures. Next one is a scale drawing. I'm sure you've done something with this in art, but scale drawings is a drawing that is similar, like we said, similar to an actual object or place. Usually it's smaller. So we think of a scale drawing, we think of a map. I have a map down here. It looks like the actual Florida, but it's much smaller. It's on a smaller scale. All right, now a scale is simply a ratio of any length on a scale drawing to the actual size. So if we look down here, the scale drawing might be, the scale is 1 to 110 miles. So it's from the actual one, which would be 110 miles, to the one on the scale drawing, which would be 1 inch. So that's our comparison. 1 inch goes with 110 miles. That's a scale. Okay. And then a scale model, we'll talk about scale models, we're talking about 3D models. Maybe you've made a model airplane before, or a model car. It's a 3D model that is similar to an actual 3D object. And you might think of just like a Matchbox car. A lot of times they are proportional or similar to an actual car, but they're very, very much smaller. Okay, those are our four terms that we're going to be using today. We're going to jump right in with just doing some examples. I think we'll have about 3 examples we're going to go through and how we can use proportions to find missing things. So just before we start this problem right here, here's 2 triangles. You can tell they look very similar. So it says a symbol with this little squiggly sign symbol, and I'll circle it right there. That means is similar to. So in the diagram, triangle ABC is similar to triangle FGH. So these 2 triangles are similar, meaning they're the same shape but not the same size. So we're going to use that here in an example with the word similar. It says finding the length of a side. So multiple choice. It says in the diagram, triangle ABC is similar to triangle DEF. What is side DE? So trying to find this side right here. So we'll make that our X. Now, with similar figures, they are also proportional. Their corresponding parts are proportional. So I'll just highlight some corresponding parts. This one right here, this blue side, you can probably tell it corresponds with the X because they're in the same location on the similar shapes. This one right here, that's BC, would be 16. That's similar to EF, which is 12. They're corresponding. The corresponding parts. And then this last one, the bottom, is corresponding with the bottom over here. Now, sometimes this is easier than other times because sometimes we have, I don't know, let's say a shape that's spun around. So you have to figure out which side is actually corresponding if they were the same shaped the same way and they were also in the same, like pointed in the same direction and whatnot. So we're going to use the corresponding parts to solve for DE. So we have the blue one. We'll say blue 10 over x. That's going to be a proportion. 10 is to x as, let's say, oh, I'm going to change that to black. Let's use the green one. We have both of those. So we have a ratio there. 16 is to 12. So if these are similar, they are also proportional, meaning if 10 to x would be the same ratio as 16 to 12. And now we have a proportion that we can just solve. So we have 10 times 12 is going to be equal to x times 16. So our equation is 120, because 10 times 12 is 120. It's equal to 16x. And then to solve for x, we divide both sides by 16. And we get whatever x is equal to. Now I'm going to, well, you know what? Yeah, I'll just pull out the calculator just to check. 120 divided by 16 says 7.5. That's what I got. And if we look up here, hey, 7.5 is A. So our answer for this one is A. Now, if you're doing this on your own on the smart slides that are on Google, you can pull this and check the work. I think I got the correct answer. Yep, it does say the answer is A. Or you can put that back where it was. All right, so that's how we can use proportions to find side lengths of similar figures. All right, now we're going to look at another example. We're going to apply it to shadows. Shadows is a great way to apply proportions. It says the sun's rays strike the building and the girl at the same angle, forming the two similar triangles. So these are similar triangles. So again, we have to figure out what are corresponding parts. We know that the shadow part, the sun part would be corresponding. That's the angle. The bottom parts would be corresponding. And then also the height of the building and the height of the girl would be corresponding as well. So we're looking for x, which is right here. So we're going to say x is to 5, because that girl's 5 feet tall. So x, the building height, is to 5, the girl's height. So, it kind of, well, we have to keep it consistent. So we have to do the building on top. So what do we know from the building? We know the bottom is 15 feet. Is to, and this should be feet, but is to 3 feet. So again, it's consistent because on the top we're dealing with the building, and on the bottom we're dealing with the girl. All right, now we have a proportion that we can solve. So with that proportion, let's just solve it using cross products. So we have x times 3, or we'll do, so 3 times x, that's equal to the other diagonal product, which would be 15 times 5. 15 times 5 is 75. That's equal to 3x. Then we just got to solve for x. One step. Divide both sides by 3. That gets us x equal to 25. So that means the height of the building is 25 feet tall. And you can kind of picture that as, if you look at here, this is times 5 difference here. So you'd multiply by 5 here. So that would mean right there you'd multiply by 5 as well. 5 times 5 is 25. So how tall is the building? 25 feet would be your answer. All right. That's problem 2. We're going to do one more problem applying these proportions. This is also using a scale model. So in science here, it says a giant model heart is shown below and to the right. So if you've ever been to like a children's museum, some fun museums have giant models of things. I think actually when I was a kid, there was a whole jungle gym that was a heart in a children's museum. So you could like climb up into the heart and go on a slide out of the heart. It was pretty cool actually. But anyway, this is a giant model of a heart. The heart is the ideal size for a person who is 170 feet tall. So if we're talking about this person right here, this is my lovely person who has that heart inside of them. This person is 170 feet tall. So that 170-foot tall person has a heart that would be 14 feet tall. So it says, about what size would you expect the heart of a man to be 6 feet tall? Of a man who is 6 feet tall. So we have to compare here, to make our own proportion. So I'm going to have you figure that out. And what would the size of the heart be? Okay, now I'm going to set up a proportion. So I'm going to do the heart size of the heart, which would be x, to the size of the person, which is 6 feet. So x feet to 6 feet. And that would be equal to, if we're putting the heart on top, we'll put the other heart on top, so it'll be 14 feet is to a 170-foot person. Okay, this is a proportion because they would be, it's a scale model. So if a person has a heart that's x feet tall, and that person is 6 feet tall, we can compare that to a person with a heart of 14 feet who is 770 feet tall. It's a really tall person. But anyway, we have a proportion now, and it's consistent. Hearts on top, person height on bottom. So let's use our cross products property. We have 170 times x is equal to 6 times 14. So it'll be 170x equals 6 times 14. So let's think. That'd be 28 times 3 would be 60, 84, I think. I'm going to say it's 84. All right, so we have a one-step equation that we can solve by dividing by 170. And you end up with x is equal to whatever 84 divided by 170. I know it seems weird, but 84 divided by 170 is probably going to be a little under a half. So we'll round it to 0.5 feet. So that would mean that if a person is 6 foot tall, the height of their heart would be around a half a foot tall. So 6 inches. And that would probably be a better way to say it. If it's a half a foot tall, you could say, or 6 inches. All right, assuming this is consistent. Okay, it's just another way that we can use proportions to help us figure something out. That's why I love proportions so much, because you can use them in so many different real life situations. All right, now before you're done, again, make sure you're taking quality notes on this. If you have to go back, feel free to take some more, but please self-assess yourself. On the goal sheet. All right. If you have any questions, write them down and bring them to class. Otherwise, those are your goals, and we'll see you next time.